The next speaker is Purushottam Sahu with the Leptogenesis, left-right symmetry, and double seesaw. So, please.
So yeah, am I audible? Yeah, okay. So thank you, the organizer, for giving me an opportunity to share our work. And actually, the schedule is like the talk is rescheduled today, and today morning I just saw that my talk is today. So yeah, so I will try. Okay, so I will talk about leptogenesis in left-right model with seesaw, double seesaw. And in last week, we have lectures on leptogenesis. And so I will briefly go through all the basics things, and then I will uh, talk about the how we can implement this leptogenesis scenario in double seesaw within the left-right model. And we already heard about left-right model in the last week lectures. So actually, this is the plan of my talk. So like we want to know the baryon symmetry of the universe, and for that the leptogenesis is one of the possible solutions. So I will talk about the requirements of the leptogenesis, which we already listened from last week, and then like the CP symmetry and how the CP symmetry depends on the Dirac-Neutrino mass matrix, and what are the possible ways to find out the structure of the Dirac-Neutrino mass matrix. For that, we use here the left-right model. So I will talk about that, and from where we derive the structure of the Yukawa matrix, MD, and then I will talk about how these low and high energy CP violations are connected, and then importance of their connections, and I will show some numerical results. So yeah, so like this is the fundamental questions that like what is the world of made of. So in ancient times, like people thought that the world is the organized in the fundamental elements like earth, air, fire, and water. And in ancient Indians mythology also, like we have the 5 basic elements, which are the space, air, fire, water, and earth. So the fundamental elements mean the object which are simple and without any internal structure. So where they are really the fundamental elements. So in lowest level, we have this standard model of the particle physics in to find out the elementary, to describe the interactions of the elementary particles. We have 4 kind of interactions, like electromagnetic interaction, which is mediated by the photon, and weak interactions, strong interactions. These are included in the standard model, and we have also the gravity. So in standard model, we have the quarks and leptons, and we have their antiparticle. So the antimatter was first introduced theoretically by Paul Dirac, and then we first experimentally observed in the cloud chamber experiment by Carl Anderson. And the neutral particles like jet bosons and photons are their own antiparticles. So the question is why our universe is matter dominance, and we know that from that when matter and antimatter meets, they annihilates, and we have only the photons and neutrino. So and there are the observations like Big Bang neutrino synthesis observations and cosmology CMB data. So the difference between baryon and antibaryons is coming out to be this, which says that like for every antibaryons, there is for 10 to the power 10 antibaryons, we have one more baryons. So to explain this asymmetry, like we have various theories, and to understand like how this asymmetry we can explain this asymmetry within the cosmological evolution of the universe. So Sakharov first proposed the conditions like one can naturally achieve matter dominance by explaining the CP invariance violations. So these are the three conditions, that first we need the violation of the baryon number, and then we have non thermal equilibrium processes, and then C and CP violation. So like within the standard model, like the B minus L is conserved and B plus L is violated, and the Cp is violated by the delta Ckm. So the departure of the thermal equilibrium can be achieved at the electroweak phase transition. But standard model fails on these two aspects, that Higgs factor does not give a strong first order phase transition, and this Ckm Cp factor, this Cp violation are very small. This is suppressed. So we need to look out for the extension of the standard model that incorporate viable source of the asymmetry, and the scenario must have the these things, that we have some new source of the Cp violations, or either new departure from thermal equilibrium and B minus L violations, or we have the modification in the electroweak phase transition. So the leptogenesis is a mechanism proposed by the Fujita and Yanagida. So that can induce a matter-antimatter asymmetry in the lepton sector, and which via some other processes like Spillern processes can be transferred to the baryon sector. So in leptogenesis, we study how the asymmetry is created in the lepton sector. So in leptogenesis, like the lepton number violations is the one of the ingredient, and this could be facilitated by the Majorana mass terms in the Lagrangian. And the C and Cp violations, this is be parameterized by the Cp asymmetry parameter, and which have dependence on the Yukawa and the structure like model framework. And then out of thermal equilibrium, which is achieved by the decaying particle with the condition that the decay rate of the particle, if it is less than the temperature of the universe at the mass of the particle at the Hubble expansion rate. So to leptogenesis to work, so we have the the decay of the leptons to like lepton number violating process, like the interference of the tree and loop level processes, and we need at least like two heavy neutrinos, and we can express this asymmetry parameter, the difference of the decay and the total decay, and the asymmetry parameter is the strength of the required asymmetry, and is usually referred as the asymmetry parameter. So like in single flavor, we can write this asymmetric parameter in terms of like the Yukawa matrices, and we can also express in terms of the Dirac mass. So we need to find out like what is the structure of this Dirac mass matrix. So in literature there are various proposals, and I like to get the what is the possible structure of this Dirac matrices. So to find out this, like we study the left-right model. So this is the the left-right symmetry is introduced to restore parity at the higher scale, and the fermion sector, like for every left-handed doublet, we have the right-handed counterparts, and if we have this left-right symmetric model with only like there are variants of the left-right model with the triplet and the doublet. So here we discuss the doublet version of the left-right model, where this left-right symmetry is broken to the standard model with this HR doublet, and then subsequent breaking is the bi-doublet. Here, if we have only these things, then because we like these right-handed neutrinos NR is come in the SU2R part, so we don't have direct Majorana mass from the right-handed neutrino, so we cannot study the leptogenesis. So that's why we introduce the additional fermions, perogenesis like sterile fermions SL, and with the help of this we can get the Majorana mass from both light active neutrino, right-handed neutrino, and the sterile one. So for that, like we study this the double seesaw mechanism. So if we see the structure of these things, like the mass matrix, so we know the type 1 seesaw mechanism. So in type 1 seesaw mechanisms, we have like you can, if you see this block, so this is only type 1 seesaw. So where like this is the Majorana mass term, and this MD and MRS are the Dirac mass terms. So if you see this 2x2 block, here you find out that if MS is heavier than MRS, then we can apply this type 1 seesaw structure once here, and then if MRS is heavier than this MD, so we can generate the mass for the, even if in the left-right model it is not present the Majorana mass for the right-handed neutrino, the addition of the sterile fermions induce the Majorana mass for the right-handed neutrino, and then if we apply seesaw again, then we have we can have the Majorana mass for the light active neutrino also. So here this metric structure is quite similar to the inverse seesaw, but the thing is that in inverse seesaw, like this ms term, this 3×3 term is very small, and then we have the pseudo Dirac heavy particles, not purely Marano. So here, like after this seesaw approximation, we have the like Marana mass from the sterile fermions, which induce the Marana mass for the right-handed neutrino, which was not previously like present in the model, and then we have the light neutrino masses, which is also Marana. So all these three are Marana in nature, and here if you see, like this mu is just like md over mrs, and ms and like md over mrs. So in literature, like if this md and mrs are related with some symmetry, some discrete symmetry, then we can directly find out that the matrix which diagonalize this light neutrino is directly proportional to the sterile neutrino. So this is called the screening, and this was proposed by these people. So if like this is basically the cancellation of the Dirac structure. So if MD and MRS are proportional, so then like the matrix which diagonalize the light neutron masses and the sterile neutron masses are the same. So we can find out the mixing matrix for the sterile fermions, which is the same as the UPMNS matrix, and then we using this screening condition, we can also find out the relation between the UN, which is the matrix which diagonalizes the right-handed neutrino in terms of the light neutrino. So for that, we use this mathematical. This is okay. This is not okay. So yeah. So like using some simple mathematics, like using the relations of the right-handed neutrino and the the screening condition, we can find out that applying the C symmetry as a left-right symmetry in this model, we can have the relation between the diagonalizing matrix, like unitary matrix, which diagonalizes the right-handed neutrino, is coming out to be same as the UPMNS matrix. So this now we can study we can relate the high energy parameter, like which is responsible for the leptogenesis, in terms of we can express in terms of the only UPMNS thing. So here you can see with this simple mathematics using the screening conditions and the mass relations of the right-handed neutrino, we can find out the Yukawa matrices, like Dirac matrices, which only depends on the like low energy parameter like UPMNS and the masses of the right-handed neutrinos and light neutrino. So like then like we use this matrix structure to find out the asymmetry, which is directly depends on the like structure of the MD, and then like here in this MD we have the CP violating Dirac phases delta, which is coming here, and then we have the Marana phases. So the importance of the connection is that like MD depends only on the neutrino oscillation parameter and the CP violating phases, like which is coming in the UPMNS thing, and the masses of the heavy and light neutrino. But this is different from the literature. In literature, we have various parameterization of the MD. So where the one parameterization is the like Kasasa-Ibarra parameterization, and in that we have some additional like degree of freedom which comes in the like this rotation matrix R. So here, like you can see, without any additional parameter, we can relate. We can So we can have we can relate the high energy processes like asymmetry studies with the low energy parameter like U nu. So here we don't need any kind of parameterizations to derive the MD. There are some other process also where one can find the structure of the MD. So now, like if we put the structure of the MD and we find out that there is no dependence on the Marana phases of the asymmetry parameter. Here you can see with the normal ordering, if we fix the like the Dirac CP phase as 0 and its best fit. So here you can see there is no dependent on the Majorana phases of the asymmetry parameter. So asymmetry parameters doesn't depend on the Majorana phases. It's only depend on the Dirac phases, and we it's the like kind of dependent. So the asymmetry parameters is depends on the Dirac phases only. And if we from the experimental type, if we have like very for normal ordering and inverted ordering, if we use the Dirac phases, and if we constrain the Dirac phases very well, then the CP asymmetry is only can be studied by the Dirac phases. There is no dependence on the Majorana phases here with the given model parameters. Now, like to we calculate the numerical values with by studying the thermal leptogenesis, and then we find out the for the like right-handed neutron masses around, if it is around 10 power 13 GeV, and then subsequent like masses of Mn2 and Mn3, the CP symmetry parameter like which is coming out to be around 10 to the power minus 4. Yeah, and after solving the Boltzmann equation, we can calculate this asymmetry, which is approximately coming out to be around 10 to the power minus 6. And then like here for inverted ordering, like this is coming around so like negative value. So here like we prefer the like normal ordering, and then we study the cosmological evaluation of the lepton asymmetry, like incorporating all the relevant decays, inverse decays, and sketching washout process for the normal ordering case. And here you can see this is the standard like the number density and the like its evolution with the temperature. So here these green lines are from the like cosmological observation data, and then this is the asymmetry in the lepton sector using the like consider model framework. And then yeah, so that's we study here. So to conclude that we develop a direct connection between low and high energy CP violation by deriving structure of the MD in the context of double seesaw in left-right model. The connection is independent of arbitrary factors and depends slowly on the neutrino oscillation parameter and heavy neutrino masses. The obtained CP asymmetry provides the value of the baryon asymmetry, which is comparable with the observational data. And we also see that in our analysis, the value of asymmetry parameters has no dependence on the Majorana phases. It's only depends on the Dirac phases. But with some other value, this dependence can be might this depend, and that deviates from the which is not in the thermal unflavored region. So we can extend this to study the impact of the non-zero Majorana phases in the flavor resonant region of the leptogenesis. And yeah, thank you.
So thank you very much. Questions, comments?
Maybe I missed it, but what kind of lepton asymmetry do you get in the end once you've got the transfer, however to call it?
Like this lepton asymmetry, which have the process like the decay, scattering, and like yeah some washout process. So yes, the decay of the right-handed neutrino.
Okay.
Other comment, questions? So maybe I have just one. I did not understand very well. You said at some point that you have the dependence on the mixed parameters, the Majorana phase, and also a sort of energy phase.
Huh?
Energy phase, you said.
Energy phase?
Yeah.
No, it doesn't depend on the Majorana phases. I just mentioned that, like, because this asymmetry is only.
No, you should come back. Wait. Yeah. This depends on you, no?
Yes.
And you say that this involves some high energy phases which require fitting to explain the observation. Which kind of high energy?
No, not high energy phases. I am saying that like this high energy, like we explain this leptogenesis, which is high energy phenomena, and we can explain this with the help of only the.
So you are not invoke something else, no?
Yes.
Okay.
Yeah, this only depend on the like low energy oscillations parameter,
Okay.
which comes in the like U nu.
Okay. Thanks. If there are no other questions, thanks again, speaker.